Hello everyone. Today we will discuss about chapter 4, which is digital transmission. In this section we will start with the digital to digital conversation. In this section, the digital to digital conversation means the conversation of digital data to digital signals. Here are three techniques to make them digital data to convert to the digital signals. These conversations can be line coding, block coding, and scrambling. First one is line coding. Line coding is the process of converting the digital data to digital signals. In line coding conversation, a sequence of bit to a digital signal. At the sender, the digital data are encoded into a digital signal, and at the receiver side, the digital data are received by the decoding, which makes the digital data signal. By this diagram, we can see that here the data is in the digital form, which is 0 and 1, which is in the sender side, and by this encoder section, this digital data is converted into digital signals, and those digital signals are sent by the link, and then the decoder receives the digital signal and again decode them to digital data. This is how the line coding works. Now, the characteristics of line coding. Signal element versus data element. Signal element. A signal element is the shortest unit of digital signals, and in data elements is the smallest element or entity of data. Here 0, 1, those are data elements, and here per signal element is this is a signal element, this is another signal element. Now, data rate versus signal rate. The data rate defines the number of data elements or bits sent in 1 second is known as data rate. Then the signal rate. The signal rate is the number of signal elements sent in 1 second is known as signal rate, where the unit is called a baud. The relationship between the data rate and signal rate is S equals to N by R. Here N is data rate and S is for signal rate. We can formulate the relationship between data rate and signal rate as S average equals to C into N into 1 by R, where N is the data rate with BPS, that means bit per second, and C is the case factor, and S is the number of signal elements in per second, and R is the number of data elements. Now the bandwidth section. The actual bandwidth of digital signal is infinite. The effective bandwidth is finite. There is a relationship between signal rate and the bandwidth rate. By this formula we have B equals to C into N into 1 by R, where the signal rate is known as baud rate. This formula is very important for mathematical questions. Now the baseline wondering. In decoding a digital signal, the receiver calculates the running average of the received signal power, and the average is called the baseline. This baseline is very important for theoretical questions. Now, what is baseline wandering? A long string of zeros and ones can cause a drift in the baseline, which is known as baseline wandering, and make it difficult for the receiver to decode correctly. Now the DC components. When the voltage level is in the digital signal is constant for a while, and the spectrum creates a very low frequency, thus the frequency is around 0, is called the DC current or direct current component. The DC component means 0 or 1 parity that can cause baseline wandering that we have discussed in previous section. Self-synchronization. A self-synchronization or synchronizing digital signal includes the timing information of data being transmitted. This can be achieved if there are transmission in the signal that alert the receive to beginning and middle or the end of the pulse. The receiving clock out of the synchronization, thus the points can be reset the clock. This is known as self-synchronization. In the self-synchronization, the synchronization happens depend on the clock by itself. So this is known as self-synchronization. Built-in error detection. It is described to have a built-in error detection capability in generate code to detect some of or all the errors that occurs during the transmission is known as the built error detection, which is a build function. Now, immunity to noise and interfaces. Another desirable code that characteristics is coded that immune to noise and the other is for interface. Now the important thing is here complexity. A complexity scheme is more costly than implement a simple one. For example, a scheme that is used for 4 signal levels is more difficult to interpret than one that is usually only 2 levels. In this section we will do some mathematical works. As in our example, we can see that the average volume of C is 1 by 2, that is half, and the bound rate is then S equals to C into N into 1 by R. Here the value of C is 1 by 2 and N is, here we can see that if the bit rate is 100 kilobits, so the value of N is 100 kbps, and then 1 by the R. R denotes here the signal element R equals to 1. So we have put here the value of R is 1. So by this calculation we can have 50,000. Here we can say that we have 50 kilobaud. Here is another example of mathematical notations. Now moving to the next, in line coding schemes we have several parts. In line coding you have unipolar section, polar section, bipolar section, multilevel section, and multi-transmission section. Unipolar is for NRZ, then polar section is for NRZ, RZ, and biphases. Bipolar section is for AMI. Multilevel is for 2B. Multi-transmission is for MLT3. Now the unipolar scheme. In a unipolar scheme, all the signal levels are on the one side of the time axis, either above or below. NRZ stands for non-return to 0. That means if we can see by this diagram that the voltage is going from 1 0 1 1 0, but you can see that no voltage is going under the 0 section. That is why this is known as not return to 0. Now the polar section or polar scheme. In polar scheme the voltage are on the both side of time axis, and for example the voltage level for 0 can be positive and the voltage level for 1 can be negative. In NRZ section we have two variants, NRZL and NRZI. In this NRZL section we can see that the voltage is going under the 0, but in NRZ the voltage is also going to the 0. So what is the difference? In this section we have some points. No inversion next bit to 0. There is no inversion section, but which is no inversion is for NRZL, and for NRZI, which denotes the inversion, here we have next bit is 1. So after inversion, you can see in this section that in the white blocks we have no next bit is 0 or no inversion, but when the bit is inversed it will denote it from this black, and next bit is obviously 1. NRZ L is for level and NRI for invert. We have already discussed those topics in this diagram. Now RZ, which stands for return to 0. In this diagram we can see that the voltage is going up from the minus section and then going to the 0, then moving to 1 and then again 0 and again moving to the minus section. In the return to 0 section, every time it feels to go with the 0. That's why it is known as return to 0. From this diagram we can easily understand that here are three values: positive, negative and 0. This is the negative section, this is the 0 section, and this is the positive section. Biphase. In this section the different system or schemes are also called the biphase scheme. In Manchester scheme, we have the Manchester scheme combines the idea of return to 0 and non-return to 0 level. In the Manchester scheme overcomes the several problems of NRZL. In this diagram we can see that if the edges are following, then we can denote it as 0, and if the edge is rising, then we can denote it as 1. So in this section, from this to this point we can say that it's 0, and from it is rising to the high section, so this is denoted as 1. This is known as Manchester scheme. Now differential Manchester scheme. In this diagram we can see that the differential Manchester scheme combines the idea of return 0 and non-return 0 inversion, which denotes as I. So we can easily say that Manchester scheme is combination of RZ and NRZL, and the different Manchester scheme combination of RZ and NRZI. So in this section, for being inversed, it is related that if the point or dot is white, then next bit is obviously 1. Then we found it as white, and next bit is obviously 1. And if it is black, then the next bit is obviously 0. Now the bipolar schemes. In bipolar encoding, sometimes is called the multilevel binary. There are three voltage levels: positive, negative and the 0 voltage. The voltage level for one data element is at the 0, while the voltage levels for other elements is alternative between positive and negative. Two variation of bipolar encodings. Here we have the AMI condition and the pseudo condition. The AMI is for alternative mark inversion. A common bipolar encoding scheme is called bipolar alternative marks inversion, which is AMI, and the AMI means the alternative 1 inversion, and a natural 0 voltage represents by the 0, and the binary 1 S is represented by the alternative position and the negative voltage. The diagram of AMI starts from the beginning level and goes up when the voltage is 1, and when it is 0 it is continuing, but when the voltage is again 1 it can go to the negative position. This is the diagram of AMI. And if we are in the pseudo section, in pseudo section we can see that a variation of AMI encoding is called pseudo ternary, that the 1 bit is encoded as a 0 voltage and the 0 bit is encoded as alternative positive and negative voltage. That's how we can see here in pseudo section we have that the 1 bit is encoded as a 0 voltage and the 0 bit is encoded as alternating positive and negative voltage. So by this diagram we can easily see about AMI and Pseudo. Multilevel schemes. In this scheme, we increase the number of data bits per symbol by increasing bit rates. We combine the two data elements into patterns like as m element to create 2 to the power m symbols. Here we have 2b by IQ section, 2 binary and 1 quaternary is known as 2b 1q. Use the data pattern size 2 and encodes the 2-bit pattern as one signal element belonging to the 4-level signal. In this section we can have this by this diagram that 0 0 denotes by -3, 0 1 is for 1 and 1 0 is for +3 and 1 1 is for +1. So by this diagram we can easily see that here we have 1 1 which is denoted by +1, then we have 0 0, that means the voltage will be -3. So there here if we in the diagram we have voltage -3, and the next one is 0 1 which denotes as -1 here, and 1 0 is for +3. So the 1 0 contains the +3 position. Now 8b by 6t, that means that 8 binary and 6 ternary. It stands for 8b 6t. By this diagram we can easily see about the configurations. There are 3 possible signal labels represented as minus, 0 and plus. That means one is positive, one is 0 and another one is the negative one. The first 8-bit pattern, which is 001 001, is encoded as a signal pattern of minus, 0, minus, then 0, then plus and plus. In this diagram we can see that 001 001, which is this pattern, and by this we will get this output as first one is minus, then 0, then again minus, then again 0, then plus plus. All the sections are doing the same. Now 4D PAM5. The 4D PAM5 is obviously similar to the previous one. You can have at a glance of this one. Now moving to the next is the multi-transition. In this section we have multi-transition 3, which is denotes for MLT3. When we have a signal with more than 2 levels, then we can design a different encoding schemes with more than 2 transmission rules. The MLT3 is one of them. Here we have 3 levels. One is the positive, then the 0 section, then the minus section. If the next bit is 0, then there is no transition. If the next bit is 1, then the current level is not 0 and the next level is 0. If the next bit is 1, then the current level is 0 and the next level is opposite of the non-zero level. Here are two cases, typical case and the worst case. In typical case we can see that we have 0 here, so the next level will be 1, and after 1 the next level will not 0 and the next level is 0. So here the next level is 0. This is how the typical case works. And then the worst case. In this section we have that all the inputs are 1. So in this section it creates a confliction that first level is in the positive section, then the next one is in the 0 section, and another one is the minus section. Then it is again going to the 0 and then again positive, again going to the 0 and again going to the negative. This is the worst case for MLT. Now By this diagram, you can easily know about unipolar, polar, bipolar, and multilevel and multi-transmissions. Have a glance of this pattern and table. Now moving to the examples, here we have a mathematical notation. Here we have S equals to n by 2. Here the given input is 500k bounds. So the B minimum is, that means the bandwidth minimum is equals to 500 kilohertz. Now we will discuss about block codings, which is the second scheme. Block coding is normally referred as an MB or NB coding. It replaces each of the M bit groups with the N bit groups. In block coding section, we have in division, and a sequence of bit is divided into groups by M bits. Then the substitution and M bit groups with the N bit groups. Then the combination with the N bit groups are combined for M streams. In this section we have all M bits, and M bits as an input. So now we will transform this M bit into N bit by substitution. Those M bits are transformed into N bits. This is the work of block coding. Those bits are worked as a block, so those are known as block coding. Now 4B and 5B section. The 4 binary and 5 binary coding scheme is known as 4B and 5B. In this section, by this diagram, we can easily see that the sender is sending the data in 4B or 5B encoding. Then the non-return 0 inverse encoding is happen, and then it is sending the digital signal, then again decoding, and then the receiver gets the output. 8B or 10B is the same thing with 8 binary and 10 binary encoding instead of 4 and 5. The 8-bit blocks are divided into 5 by 6 encoding and 3 by 4 encoding. Then it will send to the disparity controller, and then it will create a 10-bit block. The third scheme is scrambling. In the scrambling, the technique is used to create a sequence of bits has the required transmission, which have self-clocking and no low frequency with no wide bandwidth. In this section, the AMI works. The modified AMI encoding section just generates the digital signal, and then the modification of AMI decoding generates input for the schemes for the receiver. In bipolar with 8-0 substitution, which is known as B8ZS, works like this one, which is the previous level of positive and previous level of negative. In this previous level of positive section, all the section we have that the 0 is the neutral line, and in this section we have the 1 is for positive section, and in this negative section we can see that for 1 we have the negative input. HDB3 stands for high density bipolar 3-0. By this diagram we can easily understand that for first substitution we have 1 for positive value and 1 for negative value, and then 0 is for the high density bipolar 3-0. That means here the B is for 0 and 0 is for 0 and the V is for that one. Here we have the even input. From this to this condition is for the even input, and for the odd section it works, and then again from this odd section to the even section this works like this, and this even section to this even section it is worked appropriately. Now we are in the section where we need to discuss about analog to digital conversion. For the exam point of view, this conversation is very important. There are two techniques. One is pulse code modulation, which is known as PCM, and another one is delta modulation. Now the pulse code modulation is to generate pulse. In the most common technique is to change an analog signal to digital signal is called the pulse code modulation, which is known as PCM. A PCM encode have three processes. The analog signal is simple, and then a sample signal is quantized, and then the quantized value is encoded as a stream of bits. First of all, here is the analog signal, then we are sampling it, then encoding, then quantized, and then converted into a digital data. This is how the PCM works. The basic element of components of PCM. Here we have the ideal, natural, and the flat top. First is the ideal sampling, which diagram looks like this. Here we have the analog signal version, and in this natural sampling we have timing and amplitude, where the analog signal stands from there to there, and in this flat top sampling we have the diagram looks like this. You can understand the difference between those by seeing the diagram. Now look at the diagram very carefully, and you can understand what are the difference. Now here are some description of those samplings. You can just easily go through them by the slide, which I will give the link in the description below. Now the sampling rate. The sampling rate is nothing but the inversion of sampling inversion is called the sampling rate, or sampling frequency is denoted by where fs equals to 1 by t section. Here are some points about quantization. Here are some description about quantization levels and quantization errors. You can go through them. Those are used in analog to digital conversion, which is known as ADC. Now the uniform versus non-uniform. You can easily go through them. Those topics are not very important for your exam point of view, so we are not discussing this one. Encodation. Encoding is the process to make your code ready for sending, is known as encoding. This formula is important for measuring the minimum required bandwidth. Here B is for bandwidth. You can get the result in Hertz. You can practice these maths for your examination. Now the delta modulation, which is known as DM. In this section we have the PCM is different from delta modulation. In delta modulation section we have the diagram where we can see that we have generated a binary data. By this binary data we have this symbol outputs, and by these outputs we need to generate our signals, which is denoted in the blue color. Now here we will know about modulator and demodulator. The work of modulator is to transform the analog signal into digital data, and the demodulator work is to transform the digital data to the analog signal. The modulator works on the sender side and the demodulator works on the receiver side. Now the adaptive DM, that means a better performance can be achieved by the value of phi don't fixed. In this delta adaptation, the delta modulation, here the delta modulation, the value of delta is according to the amplitude of the along the signal. You can go through about this error section. The difference between PCM and DM is very important for exams. You can go through them. The PCM using 4, 8 and 16 bit, but in DM it is used for 1 bit sample. So this is a small section and this is a large section. The PCM can be fixed or variable, but in DM it is obviously fixed. The PCM is complex, but it is simple. The PCM needs highest bandwidth because it has 4 to 6 bits, but it has low bandwidth. There is no feedback in PCM, but feedback occurs in DM. Transmission modes. In data transmission modes, there are two types, in parallel and serial. In parallel section, we will discuss further, and in serial section we have three types, which are asynchronous, synchronous and isochronous. In parallel section, the data is sent as parallel section, that 0 1 1 0 1 1 0 and 1 0 is sending in the parallel section at a time. The 8 bits are sent from sender to receiver at a glance. Advantages and disadvantages of this parallel moving is given here. In the serial transmission, the input is going from the 0, then the 1, then 0, then 0, then 0, then 1, then 1, and then 0. It is going like a bus which are taking line. By line, it is going from here to there. The advantages and disadvantages of serial transmission is given below. By this diagram, you can easily compare to the serial transmission and the parallel transmissions. The isochronous section, in the isochronous transmission, it is granted that the data arrived at a fixed rate. The difference between parallel and serial are given below. The parallel is for computer to printer and the serial is for the same type of devices, that means computer to computer. This transmission is slow, but this transmission, parallel transmission, which is very fast. Here we use the clock pulse, but here not. Cost of this parallel transmission is high, but the serial transmission is very much low. Sometimes in serial transmission you can use also clock pulse, but only in a single bit. But in parallel section, the multiple bits are sent from each clock pulse. The type of serial, here we have the synchronous transmission and asynchronous transmission. In synchronous transmission we have a data flow with the full duplex mode in a form of blocks or frames. Here is a frame, here is another one, and here is another one. So the data is divided into frames and block is known as a synchronous transmission. The advantages and disadvantages are given below. In the asynchronous transmission, we can say that their data flow is flowing in the half duplex mode. So 1 byte or character at a time is a transmission the data in continuous section. So the data is going from continuous section, but for time delay and some other delays it will divide it into section in this asynchronous transmission, which can generate problem in sending data. So the advantages and disadvantages are given below. The most important question for your exam point of view is the difference between synchronous and asynchronous data transmission. In synchronous, the cost is high, and here the cost is low. The asynchronous is simple, but the synchronous is complex. It is used in full duplex mode and asynchronous in half duplex mode. Asynchronous is random, but synchronous is constant. Gap between data is absent in synchronous transmission, but asynchronous there are gaps present. Bandwidth is loss of 5% over capacity, but in asynchronous section, which is 20 to 30% over capacity. The synchronous is used in chat room and video conversation, and asynchronous is used in letter, emails, etc. You can have a snap of this one because this difference is very important for your exam point of view. No more today. Thank you.